Hello and welcome. Today we have a Leetcode premium question. This is find shortest path with key hops. So basically the question is giving you a bidirectional graph. You have like nodes from like 0 to what n-1, right? And then you can see the nodes are connected. And then you're also given a number of hops, which is key. Now, if you hop a node, or if you hop an edge, excuse me, if you hop an edge, it means you do not add the cost of that edge, to your path, basically. So, you are given two. Also, in the question, you are given two nodes, right? Your source node, which like your starting point, and then your destination, your so S and D. And you can see in the first example, right, we have at most two hops, right? K is equal to 2, S is equal to 1, D is equal to 3. So we start from S, right? And then we go, the edge connecting 1 to 0 is having a weight 4, 0 to 2 is having a weight 2, and what's 2 to 3 having a weight 6. Now, if we skipped 2, we skipped the edge between 4, uh, we skip the edge between 1 and 0, right? That means we are skipping over 4, and the same thing from 2 to 3, we skip over 3. So if we have key hops and we use our two hops in this case, right, then our total cost is what, 2 to traverse from node 1 to 3. So that's the idea. You use a number of hops, and we want basically the minimum cost also. That's how you can rephrase the question. Right? The question says we want to find the shortest path, but not just the shortest path. We want to find the minimum cost. So how are you going to select the edges, right? Knowing your key hops and get return, the one with the minimum cost. And the answer to the question of how is going to be Dijkstra's algorithm, right? This is the shortest path problem, and we have a graph, and usually if you have a graph and a shortest path problem, you should be thinking Dijkstra's, and I think Dijkstra's is very helpful in this case especially. So what we want to do with Dijkstra's algorithm is to add to our priority queue based on a certain requirement. In this case, the requirement of the edges that will add to our queue, we want the queue to sort based on the cost, right? So the parts with the least cost, like for 0 and 2, are those ones that we'll select first. So let's say we start from 1 to 0, right? I will put in two different edges. I'll put in the edge where we add 4 to our cost, right? Like let's say initially our cost is 0, where we add 4 to our cost. And I also have an edge for where we also skip over this, right? So we add all of those to our priority queue. Our priority queue is sorted by the cost, and eventually I'm going to be picking based on the ones with the least cost, and that's just algorithm will guarantee us that by the time we get to node 3, that is the least costly path basically that we've chosen, right? So we'll have the least cost returned. It's just very simple Dijkstra's. Um, so let me get into the coding basically. So first we want to create what our adjacency list, and our adjacency list will take an element we'll call an edge, and I will define it soon. And along with it, also I'll define something else so that there's a bit of a distinction, a different class I'll call node also. So class edge, right? What is going to be in our edge is the node, right? The node name and the cost, right? So public uh, takes the node and takes the cost as arguments. Now, also, I was saying that we also want a different kind of um, class of elements to be in our priority queue, right? Because our priority queue has to keep also the number of hops that we have left, right? So to modify edge in a slight way, I want to create a whole new class that is called node, right? Capital N, and that node keeps the node value, right? That I call small n, the cost, and also what the number of hops, basically, right? So that's it. So that will be in our priority queue, but for our graph, right, our adjacency list, um, the edges is what we're going to put in there, right? We're going to put edge in there, and then in our priority queue, we put in what nodes. So there's just a bit of a distinction. So this is it. So we have these two classes. Now let's just go and build our graph, right? So from we have okay, sorry, so from int I of 0 to I, and just building a normal graph, right? So for each index, I want to set um, adjacency I towards a new array list, right? Putting an empty array list, and that is what will fill with the neighboring nodes and stuff like that, right? And notice that the graph is bidirectional, right? So we can get from one edge to another, right? Like I wasn't from node 0 to 1, and basically from 1 to 0 is basically equivalent, right? So we have to add both to our to our initial graph, right? So um, let's say we extract an edge, right? Then the first element in the edge is what node 0, edge 0, right? Which is u, which kind of source in this case, and then v is what h1, and then we have also what's the weight of the edge, basically. So just come and say that adjacency for you, right, we want to add, but now I want to add a new edge. The edge will take the node value v, and then the cost will be what's w, right? And then we'll do the same thing for v, but in the reverse, where we'll have what the node value being u, right? And then the cost of the edge still being what w. So we have these two loops building graph right now. What else do we need? Basically, we need a structure to keep costs, or the minimum cost we've seen so far, and I want to call it cost, right? And here, note that my cost is going to be a 2D matrix, right? So 2D matrix, in a sense that it stores for all the nodes, right? So from 0 up to n-1, right? And it stores for all the what possible hops, right? From 0 all the way to k, right? That's why I have it as a 2D matrix. So initially with Dijkstra's algorithm, right, each element in our graphic hasn't yet been visited, right? So each array in the course, for example, then we set every element in there to be infinity, right? So say arrays dot fill, right? AR, which was integer dot max. This is Java, basically. Right, you're setting it and filling every element with what, or every row with infinity, right? And after we are done, then for cost of s, and knowing that we've not, the initial time, right? We've not used any of our k hubs, basically, right? So for s and k, then I have to set it to 0, right? The cost from starting from wherever our source node is, it shouldn't cost us anything, right? Initially, right? So like if we are at 1, we haven't, for the first example, we haven't moved, the cost should be 0, right? And then from then on, we want to add to our priority queue. And I previously explained, right? I just have a small class distinction, right? Where a priority queue is taking what node instead of edge. But you could probably even have your edge class in a way that it has hops, but I just don't want to confuse, the viewers. So I have two different classes, right? So the priority queue is going to sort based on what cost. So I'll say a dot cost minus what b dot cost is going to sort where the least cost comes first, right? Basically, it's in ascending order. Okay, because we have our priority queue right now. What do we add to our priority queue? Or for our priority queue first, we want to add a new node now, right? The node, or what's the name of the node value? It's going to start with S. That's the first one that has to be processed. And the cost at that point is what 0. And the number of hops we have is what k. We have not used any hops at this point, at least not to my knowledge, right? So then we want to write a general formula for um, basically our BFS to process everything we have here. So basically, we have actually we are pulling a node. So say I want to call it current, right? The first node at the head of our priority queue, whenever we are processing, is what we'll take first. So we'll say pq.pull, right? That is what's going to pull the first element, and that is going to be a node. So if you want to extract certain information from that, we can say, for example, that current node is should be equal to a node of current, right? And then we'll say, for example, also current cost. What is it? It's equal to current dot cost, and the same thing with the number of hops you have left. I will say current hops. So that's current hops, right? So with that said, right now, what are our base cases before we do a processing on our neighbors, right? Well, the first thing I want to check is if the current node is equal to our destination. Now, if it is as our destination, right, then according to Dijkstra's algorithm, we are guaranteed that the cost at that point is the minimum cost possible, right? So say current node, if it's equal to D, right, then I want to return this was our current cost, right? So in this case, for example, the first question would be two, um, and when that does not trigger, then what we want to do is to check, right? Now I want to check if again that our current addition makes sense in the context of our cost array, right? Like if we have a lesser cost in our array, then whatever path we are taking currently, like whatever node that we are processing, right? If there's a better path to that point, right, with a least cost, then I don't want to go through that path that we are currently on, right? Because it has a greater cost already, and that cost is less than what we have in our table, our cost array. So if so, then I don't want to go on that path, right? So I'll say for if costs of what the current node, right, we check for the current node, and then we check for a number of hops, right, because it's two-dimensional. I'm doing it for both the nodes and the hops, right? So if current of the hops, sorry, the current node and the current hops, right? If that is less than your current cost currently, then it means like there's no need for processing, right? So what we want to do is to continue, and we also do not continue. So basically, when we continue, right, we're not going to process in the rest, which is going to be what where we deal with our neighbors, right? And just before that, just before we deal with our neighbors, I want to say, okay, if um if it's not the case, or if it's the other case, right, where the current node, the the current cost, if that is greater than our current cost, right, which is the opposite, then we want to set it towards current cost, right? So this is the least cost so far. So initially it would be infinity, right? But then you set it to current cost, for example, whatever the cost might be. So maybe like from 1 to 0, the cost might be total cost might be 4, and that might be what we initially set it to. But basically just to process everything, right? And then we want to look for the neighbors of our current node, right? So say for the edge neighbor in the adjacency list of the current node, right? What do we want? Well, first again, I want to extract certain like important information. So I'll say the neighbor node, for example, right? That should go to neighbor node. Again, I need what the cost, basically the cost so far. So base number cost. Sorry, the cost at the neighbor node, basically, like to take that node, um, or that edge, basically, it was neighbor dot cost, and then again, I think okay, these are the two things we can get with the node, right? And now my question is, right, what's the new cost if we added our neighbor cost? So the new cost, I'll just keep it in a variable so it looks cleaner, right? There's going to be our neighbor's cost plus what our current cost, right? We are adding to our current cost progressively as we move on. Now, if our new cost is less than what our cost of the neighbor node, right? And then for our current costs, like if it's less, right, because if you not hop, basically if we add a neighbor's cost, that means we are not hopping, right? So we're going to use what current hops here, right? And then the node that we are working with is what neighbor node. So basically, just going to be cost neighbor node of the current house right now. If our new cost is less than that, then we have to not only update our cost array with what with the right basically the right course now. What we also want to do is to add a new node to our priority queue, right? So I'm going to be new cost, right? And then our priority queue dot add. Now what we're adding a new node where we take first the neighbor's node, right? The neighbor node, and then our cost now it was new cost, and then we number of hops is what current hops basically at that point. Cool. So as I said previously, right, we are going to simulate for using the edge, right? And also going to simulate for what not using the edge. So we're going to say, but basically we only won't use an edge with like if we have a certain number or an available number of hops that we allow basically, right? So when you check if our current hops, if that is greater than zero. Now, if it is greater than zero, that means we can reduce it by one and it will, still be valid, right? It'll still be a valid move. If it's greater than zero and right, it's a viable change to our cost array, right? Right, right. So if cost of what sorry, if cost of the neighbor node, and then what current hops, right, minus one, right? Because we are going to reduce by one. Let's say we are actually taking a path, then we're going to say current hops minus one, right? Now, if this is greater, right, than our current cost, right? And note that it's current cost and not new cost because we are skipping adding neighbor cost, right? So it's going to be like new cost is equal to what current cost basically. So now if this is greater than our current cost, right? Our current cost is less than this. It means fine, we can make a change to our cost array, right? So if we can, right, then not only do we make a change to our cost array, but we add to our priority queue. So because basically something like this, right? So yeah. Um, and then we are going to set it to current cost. And after that, our priority queue, we have a new node. We're going to take a neighbor node. It's going to take the current cost, right? And then it's going to take us current hops minus one, right? That's the number of hops we have left. Okay. So basically, it's going to run, and eventually we should hit D. And if we hit D, we return what the current score. But if it doesn't, then what we want to do is what if our for loop, our for loop breaks, I want to return negative one at the end if it doesn't check out. So this is all the code we need. I think it's never syntax error free, but cool. We have a few mistakes in there with the bugs. Okay, so a few seconds to just check them. I think I've seen the bug, right? And the bug is basically resetting the elements in the cost array. So basically, for neighbor node, we want to change for not just neighbor node, right, but the corresponding number of hops that we have. And that is supposed to be your current hops minus one. Sorry. So current hops minus one. This should do the trick. Yeah, so we pass everything. So first we were just filling in with the wrong thing. Um, okay, so it looks good for the first few cases, and then we have 100%, right? So this is one of the best solutions we have out there. I guess this is the best on Leetcode right now, at least the fastest. Um, and what's the runtime? Good question. It's going to be elog v, right? Or you can do it in terms elog v, where e is the number of edges, right? And v is the number of vertices, right? And or you could also have it this way, right? You have it in terms of nodes, right? And then it will be n log n, but all that is coming from a priority queue as normally with the Dijkstra's algorithm. I hope this video was helpful, guys. If you like it, please like the video, and I'll see you guys on the next one. Peace.